Okay, so we're going to get started here. Once again, I'm going to go start the sharing here. Today what we're going to be talking about is the first of the types of modeling methods we'll be examining for this semester, namely a technique known as system dynamics. Within the next few lectures, we'll be learning about some of the perspective of system dynamics, some of the ways in which we specify system dynamics models, and we'll be further learning about the techniques for actually building system dynamics models in two of the packages that we'll be working with this semester, to wit, AnyLogic and Vensim. And Seth has arrived here just in time with some laptops which were equipped with both of those sorts of software. Seth, maybe you could let me know, were you able to diagnose that issue with AnyLogic that students had mentioned last time?
Yeah, it was needed to be upgraded from 6.8 to 6.9.
Okay, great. So it sounds like it's probably resolved then with AnyLogic. Is that right? Okay, terrific. Thanks very much. Okay, so within today's discussion, I'm going to be spending most of the times with some of the ideas behind it, but we may fire up Vensim particularly and try making use of it. So I'm going to first talk a little bit about some of the perspectives that system dynamics offered and some of the constructs associated with system dynamics models. And we'll see if we can then have a bit of a chance to actually build up a small model that the time affords. So system dynamics is an approach and a perspective on modeling. It involves common use of a set of modeling specification mechanisms that have to do with what we call stock and flow modeling or causal loop diagrams. But it's also a perspective that on the way processes operate in the world that draws particular attention to the phenomena of feedback and of accumulation processes. Okay, so accumulation over time and feedback in the form of cases where a given change at a certain piece of the system will lead to a cascading series of changes that will either amplify that original change or will push back against that original change. We'll tend to sort of slow it down and potentially damp it out. So system dynamics involves a certain way of looking at the world and parsing how systems operate that put central attention to the processes of feedback and of accumulation. Okay? System dynamics is more a broad and over time evolving methodology to help conceptualize, describe, analyze, and manage complex systems, and particularly feedback systems. So it helps us sort of tease apart what's going on and characterize this in precise terms, to analyze it using a set of rich tools that have been built up over the decades, and a lot of attention on the management side. We're not merely observing, we are intervening in the system, and we're seeking to do so most effectively. The idea here is that the system dynamics toolboxes will help prevent us from doing the equivalent of banging our head against the wall when we're trying to get something done. We recognize how the system is working so we can interact with it in a way that will be much more effective, that will interact with it according to its sort of natural properties, take advantage of its structure, and allow us to go further. The analogy that's sometimes trotted out here is we don't want to be like King Canute. Does anyone here know the story of King Canute? Canute, no? Of ancient England. So the story was that King Canute at one point was feeling the power of his reign, and he at one point tried to go out and command the tides and the waves back. And he got a bit too caught up in his power, and he believed that he could legislate or rule over the waves. And he was sorely disappointed. He was working against the natural order of things. The waves and the tides came in and dashed his dreams. And so it is with us with a lot of complex systems. We're working at cross purposes with the system. If we can figure out sort of how the system works, the idea is that we could interact with it in a more effective way. We could take advantage of its structure instead of working against it, and more effectively accomplish our tasks, more effectively accomplish our goals. And much of what system dynamics concentrates on in this regard is the occurrences of feedback. We don't want to be in a situation where we are creating a system which is inherently unstable, which spirals off in different directions based on the vagaries of how we interact with it. We want a system which is better under control. Secondly, we want to recognize cases where there's negative feedbacks in place of these sort of balancing feedbacks, because we may be trying to do things which end up being needless, or which end up just constantly leading to a struggle, sort of like Sisyphus. How many people here know about Sisyphus? And okay, yeah, what was Sisyphus famous for? What was he famous for doing?
Pushing a rock up a hill.
Yeah, he was pushing the rock up the hill, and it was pushing back down at him, as Newton's laws of motion would tell us, right? And we don't want to be like Sisyphus, constantly pushing rocks up hills. We'd like to be able to know how to get to our destination in a more effective way. So system dynamics is a general approach, and more so than the other methodologies, it's kind of a perspective on the world, which I'll try to convey some elements of. Interestingly, and compared with the other methods, it's quite distinctive. It includes qualitative and quantitative components. The idea here is to try to deliver value to what's often a stakeholder or client, people who are dealing with the systems that we're modeling, all throughout the modeling process. It doesn't require getting to a quantitative model. It's something where you should be able to deliver some insight from the very first day that you're interacting with the client by sketching out qualitative models first and proceeding over time to quantitative models, okay? So the idea is that the modeling process is more than the model as an artifact, more than the model as a tool. It's more than this program we can run. It's a process that delivers value through constant interaction, and there's value gained from the process itself, and there's value gained from a variety of things other than the simulation model itself. So it puts a real emphasis on process and how do you work effectively across disciplinary boundaries. And there's this whole area, for example, of group model building, of how do you work with people from all sorts of backgrounds and jointly build up a model, jointly get the insights that allow that model to be created, and jointly get that feedback for that model, with the motivation being manifold, but among the major motivations, when you finally evolve that model, it's more likely to be grounded. It's more likely to be based on real-world issues because you've gotten feedback all through the process. And secondly, very importantly, people, if they've contributed to building up that model, they're more likely to buy into it. They're more likely to view it less as, I want you to use my model, and more as, oh, that's my model. I contributed to that model. This is not a small matter. For many projects, you think about highly political projects or projects that are very visible in the political domain, getting buy-in is often what allows the project to succeed versus fail. It's not so much the technical nature of the model, so much as people's attitudes towards it. And by involving them in the modeling process, we can often change their attitudes towards the better and actually build up knowledge along the way. So it's very much one that deals with the human theater. On the other hand, and this is a very interesting sort of simultaneous element, it consists of a set of formalisms that have a very strong mathematical foundation. So for those who are from physics or engineering backgrounds, who are taking courses in differential equations, I'll tell you that the mathematical specification mechanism used in system dynamics, or the mathematics that describe the systems characterized by system dynamics using what are called stock and flow models, are ordinary differential equations. And because of that, we can use a whole bunch of tools from applied math in analyzing them. We can analyze stability, we can analyze long-term behavior, we can reason about how a system will behave with wide ranges of parameter values in a way that we wouldn't be able to with an agent-based model, which we'd have to run separately for each possible combination of values. So this allows us to kind of rigorously reason about it, and it can allow us to build a set of analysis tools using ideas like control theory and Kalman filtering and a set of rich techniques. System dynamics does come with a set of evolved software that allows us to focus more on what we're describing and less on the how. You don't feel like you're describing differential equations, even though you are, because you're describing it, characterizing it in a quite intuitive graphical manner. And you're not caught in a maze of, while loops and variable declarations. You're kind of sketching out a system in terms that many people can understand directly rather than dealing with software engineering concerns. And finally, it's a set of techniques for interfacing with other areas such as statistics, etc. So those are some sort of high-level comments on system dynamics. Because this is the first of 3 techniques that we're going to be talking about in the course of this semester, I wanted to draw attention to the fact that when we're talking about these techniques, it's very important that you realize that what distinguishes these techniques, we'll see the techniques each have their own graphical language, they each have their own way of characterizing systems, each have their main points of focus, and indeed each have their own software. But ladies and gentlemen, that's not the deepest part of the differences that distinguish these approaches. The deepest part that distinguish these approaches are instead, I would argue, the questions being asked by these approaches. Okay. It's not just the answers they give that are different, or the way they get to that answer that's different. It's the questions that they ask are different, and it turns out each is suited to different sorts of questions and problems. Okay, and so you'll see different ways of framing what you might think is one problem, different ways of framing it in each of these techniques, and it bears thinking about that fact and appreciating it. It's not merely one is better than the other. They have different perspectives on it, and each of them adds something to the table. Okay, we're going to see this. Just bear it in mind as we go forward. Okay, so we have to be conscious of the fact that we're going to see differences in the language and difference in how we specify the model, difference in the software. That's a little bit. That's just part of the picture. The deeper issue is the questions. And I would particularly argue people have mapped out the sorts of questions that system dynamics is used to answer, and you'll see they've mapped it out into kind of 2 axes here. And I thought this was really interesting. This is presented with by a colleague of mine who's from EE background, but is a professor in social work, which is this really interesting combination. And he argues that the models that are built basically, and actually this comes out of other people's work too, they're distinguished by in terms of to what degree do they focus on things that are kind of more objective and based on sort of very clearly defined, well-known quantities, versus things that are more subjective and based on people's perception of things. There are certain problems where the underlying issue is not what is the case, but the fact that people are at loggerheads because they have different perspectives or different views on what's the case, or different interpretations. And so there's kind of more objective problems and less objective problems. In other words, more subjective, where the issue is more how people understand something or difference in attitudes or perspective. And then down here, there's kind of more problems that are more sort of tightly defined by, say, coordination. They involve more sort of detail-oriented questions and more defined rules. Whereas then there's some broader questions which involve, more strategic, broader sorts of issues involving choices that are less constrained. So over on the right-hand side here, you'll see problems that are sort of less constrained, but more involving sort of broad choices, and over on the left, more things that are sort of constrained. You're optimizing within a tighter set of constraints. So, for example, restructuring, system dynamics is used a lot to think about not only how is this system working, but how could we design this system so that it works more effectively? How could we put in place feedbacks so it would be more effective? Along with this kind of perspective on broad uses of modeling, system dynamics has this real emphasis on participatory methods. And because of that, system dynamics tends to use specification mechanisms for models that are purposefully more simple and that can be understood by people from a wide variety of backgrounds very readily. So that in your very first meeting with stakeholders, you could show them a model and they could say, I understand what this is depicting, and immediately start discussing it and immediately start contributing to the conversation. And this may sound odd to people from computer science background. After all, how could someone understand a program if you showed it to them the first time? I mean, programs require a lot of study and reasoning. Well, it turns out the specification language of stocks and flows that we'll be looking at is something that speaks to intuitions people have. And I have seen, with my own eyes, cases where you go show someone a model and they'll say, well, I think you're missing this link between these two factors, or you've shown something here that's not really the case. You need to separate this one stock into two stocks. So there's a real emphasis on speaking to people from a wide variety of disciplinary backgrounds and using the model as what we call a boundary object, as something that everyone can understand, point to, have a common point of reference, even if they're talking different languages. And that allows something close to a Rosetta Stone. The Rosetta Stone had, common events written in, 3 languages? Greek, Egyptian hieroglyphics, and I don't know what else. Sorry? Latin, thank you. Was it Latin? I was wondering. Sure. Wow, that would be pretty nifty. Don't you wish you were Latin scholars? So Rosetta Stone allowed people to have a common point of reference so they could translate between these things. Champollion was one of the key people there who helped formulate a way to translate. And so it is with the ideas with models in system dynamics. The model can be a common point of reference, common boundary object, which multiple people can speak about, and therefore they can start to learn how to speak each other's languages. They have something in common to talk about. Okay, so I talked about stages of the modeling process before, and I've kind of thrown up some here which relate to system dynamics. So we talked about the stages of the modeling process occurring in an iterative way. System dynamics speaks puts a tremendous amount of attention to this top one, the mental model. Needing to think about people's mental models is kind of the ultimate focus of the modeling process. This is very different from the emphasis explicitly, say, in agent-based modeling. Here in system dynamics, we are explicitly trying to change how people think about the situation. Change people's intuitions, their sense of how to react. in much the same way that you might try to, in a driver's education course, teach someone how to react better when they're driving on ice so that they don't overreact and turn the steering wheel. The idea is that we should be able to train people like that for a broad class of systems, and that we're often overreacting or interacting with it in an unfruitful way in many areas, many types of problems. It's like we're driving on ice with poor reflexes or with poor sense as to how you can most effectively do it. And so on ice, our cars, sort of fishtail around and sometimes end up in the snowbank. And so it is with many systems from a system dynamics perspective. We're ending up in proverbial snowbanks in real world because we don't understand how things work. And just like a good driving course might train someone how to drive effectively on ice or slippery roads, the idea is that a system dynamics modeling project should train people how to interact within the system, how to coordinate most effectively across groups so that you don't end up in a proverbial snowbank. Okay? That's kind of the perspective here. So this mental model is viewed as an absolutely key deliverable within this context. Now, what you also see here, shown along towards the bottom, are some artifacts that come out in system dynamics. So we have sort of certain components of each stage here. So here we have what's called a causal loop diagram, which is a semi-quantitative, mostly qualitative way of drawing out a diagram, but which allows us to reason in a semi-quantitative way about how it would behave over time in quantitative fashion. Although we can't be specific about the exact values involved, we can have a qualitative sense how it might behave. Whether it has oscillations, for example, whether it's unstable, whether it exhibits resilience to perturbation, to where we poke it, does it bounce back in a reliable way, does it have an equilibrium? These are things we can reason about with even a diagram like this in very straightforward ways. And then we have these stock and flow models, which you can barely make out, but here we have these boxes which are called stocks and represent accumulations with these flows between them that represent sort of the actions over time, changes over time in the system as people or cars or any number of different things flow from one box to another. So a box might represent people 0 to 4 years old, girls within Saskatchewan. And they might flow via aging to one, girls within Saskatchewan are 5 to 9 years old. Or you might have cars, and you have cars which are yet unsold, they're on the market, or cars under manufacturing, cars on the market, cars which have been purchased and are in use for the first time, cars which are now not in use any further. Maybe they're sitting on someone's lawn or in their acreage. There are cars that are perhaps discontinued from use but on the used auto market, cars that are used cars in operation, etc. And you might have circulation among those categories. So those would be different stocks. And for different types of situation, we have different stocks. The stocks are accumulations, and they have a mathematics associated with them that we'll be talking about not this time, but in next time and the time beyond, likely. We also have a set of mathematical lenses we can use for these models that apply tools from applied math to reason about eigenvalues and reason about the asymptotic stability of these models, whether they have a fixed point and whether they are in equilibrium, whether they're stable or unstable. And all those things pack down to very practical issues at times. For example, the issue of stability has to do with the fact that, if we're stable with respect, say, to an infectious disease, say measles, someone could fly into the Saskatoon airport with measles, and maybe they'll infect 2 or 3 other people, but it's going to peter out in the population. Just won't catch. It won't burst into a real outbreak. On the other hand, something like Ebola, there it's an unstable situation. Someone comes in the Saskatoon airport with Ebola, even though we're pretty good at tracking down contacts of infectious disease, there's a pretty good chance it'll be unstable. What do I mean by unstable? Anyone? It could lead to an epidemic. It could lead to a situation where the number of people who are ill rises very rapidly. Why do we call that unstable? Because it it leads to a situation of reinforcement where one person turns into two people, turns into four. There's a vicious cycle. And that's a characteristic of associated with instability. You get divergence. Yes?
Would you say that that's a case of the slope in mass speed? Is that simply a case of the slope being greater, less than, or 1? Or would it be more so whether it's concave up or concave down?
So it's a good question. So around a fixed point, it would be a situation where forgive me for those from different background, but the largest eigenvalue would be greater than 0. If we were discretizing it, it would be you'd have a coefficient which is sort of a multiplicative coefficient which is greater than 1, and that can lead to this divergence. But it has to do centrally with the eigenvalues, and the particular criteria is it's a non-zero. Its real component has a value greater than 0. That's what leads to this stability, this instability. Okay. Yeah. We also have situations where we sometimes simulate these models with stochastics, and we will often use them to generate various policies, shown over here on the right. And this is quite distinctive of system dynamics, because it cares so much about the human theater, engaging with people, changing how people think about it. There's a huge emphasis on building what are called learning environments. The idea is, look, just like we have flight simulators, you would never want to trust your life to a pilot, flying a plane who's never been through a flight simulator about how to fly that plane under a thunderstorm or under adverse wind conditions. The idea is that we need simulators like that for many types of conditions. So if you're a doctor and you're managing people's blood hemoglobin levels in anemia, you should be trained about how to do that. If you're a diabetic, you should be able to train yourself about how your body responds to, when you eat a piece of pie or when you are going to work out. How does your body respond to that? What's sort of the characteristics of it so that we can manage that system more effectively? So system dynamics puts a big emphasis on building these flight simulators or microworlds or learning environments. They go by different names to sort of help people train themselves on how to deal with these systems most effectively and develop intuitions for that. Okay, so that's a kind of distinctive feature. I noted that the modeling process from system dynamics perspective is one of the big focus, and the benefits of stakeholder participation I indicated. I'm not going to spend as much time in it, but there's many benefits from getting people involved with the modeling. There's many good things that come out of it, not least of which would be making sure that when the model is actually built, that people buy into it. Okay, and also the fact that you draw a lot of understanding from the model. So this type of modeling, because it's accessible, because the tools are made to be accessible, and because it puts so much emphasis on thinking about the process, it's used worldwide, in communities, some of whom may be illiterate or not even fully able to they're not able to understand some of the math behind it, but they're able to interact with these diagrams in ways that draws on effective intuition. So in this case, Peter Hoffman tells the story. This is in rural India, where they were actually drawing out for the first time. They had met these folks, and they were drawing on the board, talking about their situation and environmental degradation in India, in rural India, and how that had led to many of them losing their jobs in the local area. And this woman happened in the middle of the conversation. She kind of looked at what they were doing, looked at the diagrams, heard what they were talking, and she said, "No, you've forgotten something here. You need to have this link here. Without that, you're forgetting how these two things interact." She had never been particularly taught about it, but she was able to grok it by kind of looking at this diagram, how these causal loop diagrams work. That's not to say those are everything. There's a lot of analysis that can be done really richly, but they're an interesting feature of system dynamics that recommends it to many people. Okay, so I've just described and sort of finished my discussions here of the sort of overall perspective on system dynamics and some aspects of a glimpse of sort of different pieces of it along the modeling process. I want to now talk about some elements that are absolutely central to system dynamics, namely feedback loops, and to talk about how we build these up within these systems, because we're going to see that they're going to accompany us as a primary means of describing qualitative models, all the way up to the point where we have highly quantitative models, and we want to understand why those models behave the way they do. Why is it we see this certain behavior over time? We can parse that into a question about feedbacks. Which feedbacks are driving the system at different points? And through eigenvalue analysis and formal math involving differential equations and linear algebra, you can actually say, oh, this feedback is the dominant one here, that's why we see this behavior, then this one takes over and drives it further, and so we see this other behavior, etc. Okay, so let's talk about these feedbacks. We're going to draw these things called causal loop diagrams, and we're going to see feedbacks here as loops in the diagram. Feedbacks are central to system dynamics perspective, and so I want to speak about them and give you a glimpse of them ahead of time, and then we'll see how they emerge out of the diagrams. Qualitatively speaking, when we see a feedback, we call it a sign of reciprocal causality. So we see A, for example, as influencing B, as driving B, and B as driving A. And what this means at an intuitive level is, if we see a change to one of these, we see a change, say, to A, it leads to a change which then affects B, which then ripples around to a change to either amplify or push back against that original change in A. Okay? So we see this situation where we have this sort of causal mechanism that ripples around the system and either amplifies or damps, push back against that original change. Okay? And we're going to see that we can classify these loops in a mathematically precise sense into two types: reinforcing loops and balancing loops. And this is dependent on the sign associated with whether it leads to that original change rippling around and amplifying it or dampening it out, pushing back on it. And we'll see cases of each. Now, normally at this time in the class, I like to actually have a physical demonstration. I'm just kicking myself for not having done this before. How many people in here have ever tried to balance a broomstick on your finger or something like that? Okay, so it's an interesting process, right? So how many minutes can you balance it for? How many seconds? Anyone? Anyone done it for over a minute? No? Okay. 15 seconds? Yeah, okay. It's much easier to do with the long one, right? Now, what am I doing there? Why am I able to keep it up there? I'm exercising negative feedback. I'm actually changing the location of my hand artfully, looking at what's going. Not very good, right? It's not very artful. To cancel out the sort of movement of this thing so that I can keep it balanced. Without that feedback in place, without that balancing attempt to sort of compensate for the movement of this thing, I couldn't keep it going for 1 second, right? Okay, I'm going to close my eyes now. Normally I ask someone from the students to do this, but in this case they get in chalk all over themselves. So, if I close my eyes here, oh man, I'm dead in the water, right? I don't know which way it's going. I can't compensate for it. So it's much more dramatic when you have a long broomstick, because you have time to kind of see where it's going, and there are people who get really good at this and can do it for minutes on end. And the point here is that it makes all the world that feedback's in place. It's night and day. And similarly, I would argue that in weather like we had last week, it made all the difference in the world that we have thermoregulation within our bodies. we have a situation where our bodies compensate for changes in the physical environment in the form of lower temperatures, raise our metabolic rate, and help keep us warm in the case of adverse weather, in case of cold weather. And again, it would make a world of difference if that were jeopardized. When we feed ourselves, when we are thirsty and go get a drink. These are all cases of situations where feedback is absolutely central to maintaining these our activities. When you're driving, probably people here are really familiar with Regina. Yeah. Okay, great. So if you drive down to Regina, could you drive down to Regina with your eyes closed? Yeah, exactly. So even with situations where we know the way very, very well, there is some feedback we're constantly using to keep us on the road, for example, right? And certainly, I would be hesitant to be on the road with you unless you had your eyes open, because sometimes there's things called other cars on the road, even here in Saskatchewan, although they're often far away, right? So here we have a situation where, once again, you may know very well what's required, but feedback adds the world to the situation. By the way, we'll try to later in this class come back to that point and note that models coupled with feedback involving data, where the model gets corrected by new data as it comes in, is absolutely a very viable strategy. In fact, system dynamics models, the fact that they can be mathematically specified with precision, allows us to do that process very effectively using a technique known as Kalman filtering. But they're also amenable to other techniques such as particle filtering, which don't require some of those mathematical underpinnings. I think I'll skip this. I just want to note that from a system dynamics perspective, neglecting feedbacks is at the heart of many problems in the world. The fact that we're working at cross purposes with the way things are, it leads us to the fact that we don't understand there's feedbacks in place, for example, involving smoking. I'd used this example before, right? We lower the nicotine in cigarettes, and people end up smoking more cigarettes to get the same amount of nicotine. They've got that negative feedback. They want to get that same nicotine buzz and they're going to get it. There's a feedback involved there. There's a feedback involved with cigarettes and quitting. It may be that people who smoke will be better off with low tar cigarettes, but they're less likely to quit. So again, there's a feedback compensatory effect. So I want to start introducing the causal loop diagram so we can talk explicitly about feedbacks in a graphical sense. So I've drawn up here a causal loop diagram which depicts a feedback in its simple form, and we see the feedback shown here at the central point. And I want to talk about where this comes from and some of the meanings behind this diagram. So if we link a variable x to y within this diagram, we say x is connected to y, and we show an arrow between them. Here, what we're asking about is, what we're talking about is a situation where a change in x leads to a change in y at a causal level. We're trying to articulate things here about the causal structure of the world. We speak about causal modeling. System dynamics is an example, like agent-based modeling and discrete event modeling, as being about causal modeling. So we're characterizing, if we changed x, all other things being equal, y would tend to change. Okay? That's what a link here between the means. And we're going to label that link with a polarity plus or minus according to something that boils down to, for those who are mathematically inclined, to partial derivatives. Okay? So here, to figure out that polarity, we'll ask, okay, if x were to change, all other things being equal, would y tend to increase, in which case we'll have plus, or decrease, in which case we'll have minus, compared to the value it otherwise would have held? Okay? So let's go back to that diagram of the causal loop diagram here. So the plus here Can anyone give me an intuition? Why do we label the plus here for the link between hunger and food ingested? Anyone?
The hungrier you are, the more food you're going to want to eat.
Right. And the more food you will eat, all other things being equal. So in other words, food ingested would tend to be higher than the value it otherwise would have had. So if hunger increases, the food we increased will tend to be higher than the value it would have otherwise had. Why is there a negative link between food ingested and hunger?
As you eat, you become less hungry.
Okay, good. So the more food we ingest, it means hunger will tend to be lower than the value it otherwise would have held, right? So we can explain these things in mathematical terms by talking about partial derivatives. The partial derivative of food ingested with respect to hunger, whether it's greater than or less than 0. Okay, this is formally what this boils down to, but we can reason about it as I say intuitively here. And gosh, this is quite horrendous. Let me make this at least have some modicum of readability there. So with an arrow with a positive sign, what that means is from x to y, see? All else remaining equal, an increase in x tends to, for plus, increase the second variable above the value it would have had. And I don't know why these things are in there. That's horrible. So forgive me for including those. And here we're going to have decrease there. Increases the second variable. Okay, so actually it's better to think of it this way. Sorry, folks, but this is English up with which I will not put. Okay, so there we go. So x to y, if it's a plus, if we increase x, it'll tend to increase y compared to the value it otherwise would have had. By contrast, if we have a negative sign between the two associated with the arrow, all else remaining equal, an increase to x will tend to decrease. God, that's I will not put up with that either. Tend to decrease y below the value it otherwise would have had. So it'll tend to depress it. It'll tend to reduce it compared to the value it would have otherwise have had. Okay. So I think I'll leave that. So we're going to be building up these causal diagrams out of pieces here, okay? And these pieces will be strung together one by one, and eventually they'll form pathways and loops, okay, between things. And it's worth reasoning about the nature of these pathways. I think I have some slides that will, I don't, so we'll have to operate on it here. So here we have a situation, for example, okay, this is about, gosh, I thought I had those slides ready here for deployment, but we may label a particular link with a polarity, and often then we have links between other variables. So, for example, in this case, overtime down here is linked to fatigue, and fatigue is linked to efficiency. And that leads to a pathway between overtime and efficiency, which we could also say is associated with a polarity. So if we have a plus link from overtime to fatigue and a negative link from fatigue to efficiency, what's the implication for the polarity associated going from overtime to efficiency? Anyone? It's negative. And in fact, it's based on the product of the signs. So if you have two positives, the link has a polarity that's positive. If you have two negatives, the link has a polarity that is positive also. Why is that? Well, imagine if we have two links in a row. So we have, x leading to y with a negative polarity and y leading to z with a negative polarity. If we increase x, it will tend to lower y compared to the values that it otherwise would have had, right? And remember that an increase in y would have led to z to be lower than it otherwise would have had, and a decrease in y will tend to lead to z to be higher than it otherwise, just the opposite. And so we have a net link from x to z that's plus overall. So when we have these pathways, we get this kind of composition of polarities. We string them together, and we get a polarity out for the overall path that's based on the product of the signs for the subpaths. Okay, that, ladies and gentlemen, then leads to feedbacks, directly to feedbacks, because the polarity associated with the feedback is simply the polarity of the path from, say, here at the bottom, from level of risk all the way back to level of risk again, okay? To make a case very simple here, if we think about a retail domain situation where a company is seeking customers, and the more customers it gets, the more word of mouth sales, and the more word of mouth sales they get, the more customers it get. So we can think of this as a pathway from customers back to pathways, back to customers, and it's associated with a polarity that's the pathway polarity. That's the product of the signs of each of these, which is plus. Does that make sense to people? Okay. So let's talk about some things, further explicate this. One thing is we'll find sometimes that we don't have a clear polarity between two variables. So, for example, overtime and work accomplished per day. If I were to ask you, is that positive or is it negative? You'd be right to challenge my question. You'd be right to say that doesn't deserve a categorical answer. It's neither strictly plus nor negative. Sometimes it's plus, sometimes it's negative. When we see that, we'll unpack it. I'll be with you just a second. We unpack it into more pieces. It's often an indication there are several pathways, causally speaking here, and we need to unpack it into those several pathways to be clear about the several links. And so I've done that here, going from this to this lower diagram here. So we've said, rather than attempting to say overtime leads to more work accomplished per day, if we increase overtime, it leads to more work accomplished per day than it otherwise would have had. Instead, we unpack it. It's more complex than that. Overtime, for example, may lead to fatigue, and fatigue can lower efficiency. And efficiency, of course, itself is associated with more work accomplished per day. But this net path up here is net what? Negative or positive? Top one. Negative. Similarly, you spend overtime. This is a very real effect. It's not a small effect on real software projects. For example, people are working overtime, so they incorporate outside tasks at work. They get on the horn, to make personal phone calls. They're doing a lot more stuff they would have done outside of work, during work, arranging for babysitter, whatever, all sorts of stuff, and their efficiency goes down because of it at work, and hence it's less work accomplished per day than you would have thought. On the other hand, overtime does lead to more time working, and those more hours, and by itself, all of the things being equal, that pathway tends to lead to more work accomplished. So that you have these sort of multiple types of effect. You'll notice that there's a double hash here. We use that to indicate a delay. A situation where there's a delay in place between overtime and fatigue. And this is a well-known fact. Fatigue takes time to build up. And actually, there's some very nice system dynamics models showing this. Modeling fatigue as a stop and showing how it changes over time. And it reflects the fact, incidentally, that fatigue is a physiological phenomenon that people have tried to quantify with indices, and you can actually quantify over time the amount of time it takes to reach a certain level of fatigue. It's notable that this effect is oft ignored in some sorts of projects, so people pay attention to this effect, and eventually this effect starts to dominate, and you start to get less work accomplished per day. I would also note for software development, there's a key piece missing here in this equation in terms of the work accomplished per day. Can anyone tell me what's a key element in software or other knowledge-intensive industries that would need to be considered here beyond just efficiency? It's the Yeah, productivity in terms of quality of work. Because the problem is, if you're working lots of extra hours in a fatigued way, you may be, even if you're fairly efficient, chunking through the work, if you're introducing bugs, logical reasoning errors because you're too tired to think about them, or if you're slower in debugging, this can really lower the amount of work you accomplish per day. And what's worse, ladies and gentlemen, and this is key, there's actually some wonderful work here applying system dynamics to software development that focuses on this issue. It's easy to fool ourselves that we're ahead of the game. We're cranking out code, we're working 16-hour days, 18-hour days, code is cranking out. And of course, what we don't see is the bugs piling up, because we haven't diagnosed them yet. And by the time we hit them, it's often too late, in the sense that we promised a certain delivery date and so on, and now we've got to work through the bugs, and we've been operating on borrowed time. We've been fooling ourselves to think we're ahead, maybe making promises to the client, and now we're in a really bad way. We're in really bad straits. So unpacking these things is sometimes important, but there was a question earlier.
It was exactly about the double bars.
Okay, yeah. So that indicates a delay here. Okay. We can diagram out diagrams in this way that to sketch out our understanding. It bears noting that these diagrams can offer a lot of value for discussions with stakeholders, even if we never get to the point of having a fully quantified simulation model that includes all of them. And some of them may include factors that we know they're important, it's just they're hard to quantify, hard to really unpack, and maybe there's not a lot of data that firmly supports them. But they're about things that we know are important. We know that 0 is the one value they don't have. And so we don't tend to leave things out just because they're hard to quantify. We know that they're very important even if we don't know exactly how they're influencing things. So we tend to put them in. This is part of the philosophy of system dynamics. Put it in even if you're unsure about exact values, particularly in these qualitative diagrams. Different philosophy, some from agent-based modeling, etc. I'm trying to present a system dynamics perspective, different from statistics or what have you. So here we have a situation in the health area, substance abuse. The level of substance abuse. You can see it's a little bit of a vague term. What's most critical is that every variable in the model, ladies and gentlemen, should have a clear polarity associated. We need to be able to say, is it meaningful to talk about more of it and less than that? If it's just something like color, okay, what does it mean that color is greater? Like, is blue greater than red? You could talk about intensity of color or saturation of color, but putting in a diagram where we use terms that don't have a clear polarity is not going to be helpful. We want all variables to have a polarity associated with it. Here we are putting in some things like level of substance abuse. Really, this should be labeled probably level of substance abuse. And the idea is that, substance abuse leads to a variety of outcomes. One is it lends to more risk of injury and accidents, which leads to costs and can enhance poverty. You think about someone in the States, particularly without insurance, without any sort of medical insurance, and they get injured, they have to bear costs, it drains their savings, and there's a greater chance of poverty, which may trap them in other ways. Or, it interferes with nutrition, which interferes with health, which lowers employability, which impacts poverty. But the health also impacts stress levels, which may lead people to have this impulse towards self-medication, towards substance abuse, which leads to further worsening a cycle of alcoholism or drug use or what have you. Similarly, it undercuts, substance abuse undercuts capacity for productive work, which leads to problems with employability, unreliability. People don't want to employ them, don't want to be around them, consider them at risk or a liability, and that leads to poverty and again dysphoria and stress and so substance abuse. So we could articulate in this sort of language, in these sort of causal loop diagrams, we can articulate sort of our understanding of certain problems in a way that is not yet fully quantified, but is very rich in terms of what it can express. In this case, we've expressed it in some ways the vicious cycles associated with linking up substance abuse and poverty, for example. Okay, we're going to see that when it comes to quantitative models, we're going to need to really unpack some of these things, and it may be very hard to include factors such as dysphoria, stress, without turning into something very specific. We'd have to be more specific about what we mean by health. But at a rough level, we can sketch these things out. And it's exactly these diagrams, for example, that are often used in that rural, group model building in rural India, because people can relate to this. And they can understand, the vicious cycle here, that's trapping people, that's leading to worsening over time of the conditions. And they're quite useful for looking at outcomes here. Now, we're going to be talking about two types of feedback: balancing feedback and reinforcing feedback. The balancing feedback are the feedbacks that are associated with, well, you tell me. If we have a negative feedback versus a positive feedback, it's an indication of the polarity associated with the feedback. Whether it's A leads to B, back to A with a negative sign or a positive sign. Tell me which of these is more likely to lead to stability. In other words, a situation where a given change pushes back on itself. Which of them is more likely to lead to stability? Negative feedback. Yeah. It leads to a situation where an increase in A leads to an increase in B compared to the values it would have had otherwise. But that increase in B leads to a decrease in A. It pushes back against that original change. It doesn't necessarily cancel it out entirely. That will depend on the precise nature of this feedback and the numerical values involved. But it will push back against it. Think about that situation where you're thirsty and you want to go get a drink of water and you're no longer thirsty, right? Negative feedback. Positive feedback, does that lead to stability or instability? Instability. A little change introduced in A will lead to increase. So if we increase A slightly, it'll increase B, tend to increase B, which will tend to further increase A. And so we can very easily get this situation where it spirals out of control. Just that original change leads to a larger change in B, a larger change in A, larger change in A, and it's like spread of infection, right? From one person infected in the population to 2, to 4, to 8. It's like rabbits multiplying, right? Going from a litter from two rabbits, not one. 2 rabbits to you folks can tell me probably better than I know. So 4 rabbits beget, form more buddies, which lead to a total of 8 rabbits, 16, etc. And it just goes on and on and on. So we can have this reinforcement going on and on and on in terms of the number of in terms of the effect. So that's instability. A small perturbation, a small disturbance leads to a larger and larger disturbance over time that propagates and leads the system to be driven further and further away from its original values. Where do we see that? And give me another example in life where we see that. Where do we see positive feedback? Sometimes this is even so familiar that some people even just call it feedback. Oh man, you're getting feedback. Turn down the volume. Speaker and microphone. Right? That little original noise. Well, you'd love to hear me imitate it, I thought, but I'm not going to do that. But it leads to louder and louder and louder. Maybe you think that's like me, but during the lecture. But yeah, so you get feedbacks there. We get feedbacks. Well, let me ask you this. Let me ask you this. So I've just presented a bunch of cases of infectious disease, speakers pumping out sound. So and I've talked about homeostasis and getting a drink of water and keeping our bodies in balance. thermically and in terms of food intake and all those good things. Being tired and getting sleep, all these good negative feedbacks. So are negative feedbacks good?
Yes.
Sometimes. They can be good, and there's a lot of them that are good because they keep our system in a balance of sorts. But there are cases where there can be negative feedbacks which are actually very adverse. Cases where we have a situation where people try to escape from poverty and try to increase their income, and it ends up worsening their spending, and they end up back at the same level of wealth or what have you. So there are cases where we can have undesirable and desirable feedbacks of both sorts. So I'll just mention a few of these of each at a high level. So a balancing feedback can be very desirable because it secures resiliency. It gives robustness. It means we can go into a wide variety of temperatures, for example, and still be alive, right? So when we were out in that minus 35 degree weather 2 weeks ago or what have you, you may not have felt alive during all of that, but no, it allows us to live. In contrast to a iguana or something, or a snake, which needs to go into hibernacula and engage in, go into balls and self-regulate through the insulation of other snakes. Balancing feedbacks can lead to desirable effects in terms of robustness. They lead to a situation which is hard to disturb. I could keep that broom handle going, for quite some time because of negative feedbacks. I could keep it. It could be more robust to the gusts of wind or what have you. Negative feedbacks allow us to build robust systems. And some of the most effective things you can do in terms of system design to build robust systems are to put in place feedback mechanisms in the form of negative feedback to cancel out effects. So, what's a negative feedback that all of you have right now, at least I hope you have, in your domiciles, in your homes? What's a negative feedback you're depending on day in, day out, night and day, whenever you're at home? You're depending on a certain negative feedback. Speak to me about what it is. And it involves the home rather than you. It's the thermostat in the furnace. It senses the temperature is too low and it turns on the furnace. Absolutely central, and it makes the home robust, right? Robust to fluctuations in outside temperatures that would otherwise be highly problematic. And so often we structure interventions in real-world systems to achieve robustness by introducing negative feedback loops, right? Stands to reason. If we can architect in a negative feedback, if we could put into place a notification mechanism that our customers are unhappy, if we could listen to Twitter, see what people are saying about our company, then we could respond more effectively. We can listen to what our customers are saying on blogs and so on. We can respond. That could allow us to run a more effective company, right? If we can put into place mechanisms that allow us to look on Google and people are searching for flu-like symptoms, maybe we can recognize when flu is circulating faster than we otherwise would. We could take action in the form of advisories, encourage vaccination, or what have you. Okay, so we often design interventions putting into place negative feedbacks, balancing feedbacks. Negative is not bad. It's balance. It means it's the mathematics of it, and here it's balancing. Okay, there can be undesirable feedbacks. You can get situations where you get lock-in. People can't escape from the situation. That an attempt to escape, attempt to increase the income leads to a set of processes that deflate that original attempt. Put into place some program, and it leads to policy resistance, and so it fails to achieve its goals. These things can be quite notable, and they lead to lock-in, and these are very real phenomena. So I mentioned, in software projects, software development projects, you can get a lock-in phenomenon where a system that was humming along through a set of bad decisions on the part of a manager, gets into a situation where, say, the manager is neglecting risk management. And so fires start to come up, and you're always dealing with these fires, and so you don't have time to do risk management. And now you're locked into this situation where risk management is not done. Maybe the code base is, because of the constant distraction and so on from customer complaints, you're not able to really produce code effectively. The code base is suffering. And you can get situations where you've been locked into a new regime, as we say. And we'll see that mathematically, or we'll see that in terms of some of the intuition when we look at some of the systems that we're dealing with. So this lock-in effect can be quite pronounced. You think about the feedbacks involved in nicotine and keeping people addicted, needing to smoke a cigarette. Okay, on the other hand, reinforcing feedback, some of them can be desirable. We can sometimes want reinforcing feedback, say, to spread good ideas, to spread innovations around. We can want, if we're a company, we want reinforcing feedbacks to spread word of mouth about our products. We want a satisfied customer to tell 5 other people who want to buy it, and they become satisfied customers, and it just grows and grows and grows, right? Often companies aim for that. They aim for their product going viral so that people are talking about it and spreading the understanding, etc. On the other hand, you can get reinforcing feedbacks in the form of vicious cycles, which are highly deleterious. And if you look at people's comments, these are from Bill Gates, and they're dated here, but they're talking about exactly feedbacks. Why? Because feedbacks are what drive a lot of basic system behavior, folks. If you look at how systems behave, and this is why system dynamics focuses on feedbacks. They're not some odd mechanism out there, just some curiosity about the situation that's intellectually interesting. They are primary drivers for why systems behave the way they do. So, you look at Gates, and he was obviously parsing things in terms of feedbacks. The more users the internet gets, the more content it gets, the more users it gets, right? Where he talks about it's all about scale, economies, and market share. When you're shipping 1 million units a month of the software, you can afford to spend $3 million a year improving it and still sell it at a low price. Biggest advantage we have is good developers like to work with good developers. These are feedbacks that are being talked about here. And the feedbacks are fundamental in shaping a lot of systems' behaviors. Our temperature, in our bodies has a fundamental determinant in feedbacks. If you were to avoid looking at feedbacks, you'd be fooling yourself. You wouldn't nearly anticipate the level of robustness we have. And if we want to build robust systems, whether it's a company or a healthcare system, we need to think about the feedbacks, because the feedbacks are going to be primary determinants of whether it's successful or not. Okay, so I put a lot of examples here, and some of these are things that I've seen in practice. I remember one time I was running a site. This is years back. I was running a site which involved downloading of audio, and it was getting very popular. So people started coming to the site, and they were clicking on particular things to download. This is not a streaming site, so we had to download it to them. And the bandwidth was limited. We weren't paying for good enough bandwidth. And as a result, it was popular, so there was a longer time per download. So people started to experience long time per download. And guess what they did? You might think the negative feedback would dominate. They'd just leave the site and I'd lose them as visitors. But instead, what they would do is, well, look, it's going to take a long time. You might as well get 10 of them, right? Might as well get 100 of them at the same time. They're going to be waiting. If they can't hear it immediately, what the hell? Let's just download 100 of them. And so people start to download more things at the same time. And so it went, and this was it was bizarre. It was like almost overnight. It went from a situation where it was manageable to a situation where it was totally clogged, constantly clogged. And a given user was downloading 50 things at the same time. 50, 50, 50, 50 for all these different users. Vicious cycle, folks. On the other hand, you have very virtuous cycles. The more existing users you have, the greater the chance it will be cross-listed on other sites, or these days, more to the point, the further up it will be in Google's ratings, further up it will be in Google's search hits, and the more people will come there, right? So fortunately, I benefited from this phenomenon with the videos I actually put out there. But one of the bizarre things is that it bit me the wrong way. So when I was teaching a version of the 858 last term, I went to Google some information about some particular feature in any logic. So a student asked me in class, how do I use this? I couldn't remember the exact syntax, so I went to Google it online, and all I got was my videos listed. He doesn't know. Don't ask him. I know he doesn't know anything about it. So thanks very much. Anyway, so here's some feedback diagrams. These actually, a lot of these have to do with project management. For those who are interested in software project management, this explains a number of them. I've seen this case in my consulting situation where a project is taking a long time. Therefore, there's more change requests that come in from the customer during that time because they're not delivering anytime soon. So more change requests come in, and that increases the amount of remaining work, and that distends the project time, and it just leads to this vicious cycle here. And they don't deliver. And in fact, I don't think they ever delivered, because they got caught up in this. Another thing, this is a really unfortunate one, and it again shows the situations where you have two cancellations. Project management. Oh, good man, I saw this. It was a bad situation. Project manager, who people start to distrust, right? And the project manager was getting overbearing, and so people didn't want to share information with the project manager, and so the project manager started to get suspicious about them, started to be more overbearing, and you get this situation where there's project manager goes one way, and the team members go the other, and the project manager can't get good information on the team members, and the team members don't want to give time of day to the project manager, and it's bad news. So these are very real effects. This is from a book on quality software engineering up here. Okay, so we have virtual. Oh, okay, so I think I'll leave that. I will note that in the context of project management, these things are particularly central. So if we want to understand dysfunction at the level of projects, be they software projects, the ones most directly familiar to me, but you could take many types of projects from around industry or other areas, we can articulate them very effectively with these sort of diagrams. So the more unmanaged risk, the more schedule disruption, less time that's taken for risk assessment, and therefore the more unmanaged risks. Vicious cycles, cutting corners, right? So time pressure in software development, people skip Q&A, they skip the peer review because they're too much under pressure. I don't have time to do your peer review in your code, I've got to crank out code. I don't have time to do really thorough testing. I've got to get this thing that was due yesterday. I've got to get it to the customer now. And what that leads to ultimately is more fault ship, which leads to more complaints from customers, which lead to emergency interruptions from customers, which leads to more time pressure. Once again, you're always fighting fires. You're fighting fires from customer requests, or you're fighting fires from unmanaged risks, and you're therefore not able to do a good job with quality assurance. Quality assurance of your code. Here's another one, overload, fatigue, depression, and low productivity, and people get caught up in this, and it's hard to break out of it. One of the things I want to leave you with, though, here, and I'll come back to this. I think, yes, exactly. I want to leave you with a high-level point here, and then we'll just get a quick glimpse of things we'll be seeing next time and how this gets into the quantitative form of things. Is when it comes to projects, ladies and gentlemen, this is one of the more important points of practical learning from this course in terms of sort of a little case application. What you'll find is that when you're dealing with systems, often our systems, our human systems, have both positive and negative feedbacks associated with them. So negative feedbacks associated with project management are feedbacks associated with things that are fatigue-reducing activities. you get the team together to go see a movie together, or you have a potluck, or you have some sort of activity that's, you play volleyball together, some sort of morale-building activities, or fatigue-reducing activities, which could be people can go for a run, or they can do yoga, or they can, enjoy time at the symphony, or what have you. And this is how people counteract fatigue often. They go on vacation, right? And morale-building activities, this is how we have the team. We deal with the rough spots, the rough edges of people on the team by having the team do morale-building activities together. And these are often built into the system for very good reasons, because when there's pressure and stress, it's important that the team heal. And it's important that the team, come back together. I'm using words almost that directly connote negative feedback, right? Balancing feedback, healing process, or coming back together after disagreements. And what I want to communicate to you is one of the most dangerous things about decision-making in these systems. And again, if there's one or two things you come away from this area of the course with, it would be good if it were this one. Because we see this pattern again and again and again, and it's disastrous and dangerous, and yet it's the area people are predisposed to. What happens in this diagram that's different when the system gets under pressure and you have a manager that isn't clued in to the system's nature of the phenomenon? What do they change in the system to try to get the project back on track? What's that?
Overtime.
They put in overtime, and what do they cut out?
The activities.
The activities. So and by the way, I've been on projects like this. I remember a memo that went out, no vacation for over 1 day, in the next 6 months, something like that, or, without prior permission. And, preventing people from going to each other's offices to talk in friendly ways. They could only go to each other's offices to conduct business. So you cut out morale-building activities. You say, we don't have time for playing volleyball. Are you kidding? We're 2 weeks behind in delivering this project. No time for foosball anymore. I mean, cut out the nonsense. We've got to deliver this thing, and we're behind. Or, you got to work, I expect you to be here, 16 out of the 18 hours. You could take 8 hours to sleep and for your family, that's it. So you cut out the fatigue-reducing activities. What are you cutting out of this system? You're cutting out the balancing feedbacks. And that's not the way to bring a system back into line. It leads it to be even more unstable, even more divergent. It leads the reinforcing feedbacks, the vicious cycles involved here with overload, low productivity, fatigue, those are just much worsened. You've cut out the things which allow it to have some modicum of chance of sticking together. And that's when all hell tends to break loose. That's when you have people starting to resign. That's when you have people burning out and leaving the industry. That's when you have people quitting. And that's when you have situations where hell breaks out on the quality side, because now you've got to hire a whole bunch of people who don't know jack about the code base, and the people who have written that code base are fatigued as all get out. So one of the worst things you can do is to ignore the balancing nature of these feedbacks, cut them out, leads to this instability, and it leads to lack of robustness to these external conditions. Instead, you should actually be encouraging some of these things to lower the real causes of the problem. Fundamentally, what you've dealt with is you've dealt with the symptom and not the cause. You've dealt with the fact that we're behind by trying to paper over the causes and trying to cut out the things which cost a little bit of time. But you've ignored the systemic nature of what's going on, that the real drivers for being behind, the causes for it are what you have to deal with. And the causes have to do with overload and fatigue and people's morale levels and so on. And those are only going to be worse. If people walk out the door, it ain't going to help morale to see your friends walk out the door. People are fatigued as all get out and start to fight each other or to blame each other. That ain't going to help morale either. And that's not going to help people's productivity levels, their ability to coordinate, or the level of overload they feel. So what I'm saying is that when it comes to projects as well as to many other areas, we tend to think in a very short-term, narrow way. As Chinese say, 树木图光. You see only 1 inch in front of your nose. And you end up damaging the things that actually are critical for dealing with the underlying causes because you're caught up in the symptomology. You're caught up in the short-term solution. That, ladies and gentlemen, is a disastrous policy. And that's exactly the sort of thing that system dynamics tries to change people's mental model of. Try to shift it from the short term, how are we spending our time, that's 2 hours too much on foosball, to looking what's driving the system here and how can we most effectively bring that under control. So when it comes to project management, recognizing the negative and positive feedbacks, and in this case, the stabilizing nature of the negative feedbacks is key. But I just want to close here with a few words as a pointer to next time, pointing out the fact that while we've been talking about these mostly qualitative things, these feedbacks involving these loops, positive and negative, and glossing over the issue of exactly the strength of that feedback or this connection, the exact functional relationship. It turns out that if we understand the underlying math behind it, particularly with the issue of partial derivatives and so on, we can actually work out that there's commonly behaviors associated with these feedbacks. And the most classic behavior associated with a positive feedback is a behavior associated with instability in the form of exponential growth. A change to increase in customers leads to a change in word-of-mouth sales, which further increases customers. You've got a situation where the original change pushes back, reinforces itself, reinforces itself, reinforces itself, and it's like that microphone, the sound from the microphone and the speakers growing, 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 like that. There you got it. So this is a positive feedback, and we often see exponential growth like that. The exact exponent and whether it involves some other terms may differ a bit, but it's reinforcing in that way. We have it grow faster and faster and faster. By contrast, if we have negative loops, what we tend to have is a situation of a pull towards equilibrium, a pull towards a stasis, a balance point, where a given perturbation, a given push against the system will lead the system to bounce back. It will lead it to be resilient. It will lead to elasticity, just like that, where it will pull back against a change. The harder we push, we pull at it, the more it will pull back, and it tends to lead to the situation where we have a sort of trajectory that leads to some equilibrium. Think about homeostasis, leading to an equilibrium in terms of our natural body temperature or our level of satiation, the amount of water in our body. This is a similar phenomenon. Now, a negative feedback with a delay, for example, a delay when you think about that negative feedback, you're driving along the road, you're constantly looking, how far am I over, and readjusting, right? But if there's a delay in it, and noticing what's going on, say you're driving on ice, it's easy to get into a situation where you overcompensate, but it takes a bit of time to realize you've overcompensated. You're going too much, and then you start to turn the other way, and it takes a bit of time, and you get a delay, and that's where you get these sort of oscillations coming up. There's a delay in the middle in terms of dealing with it, so that feedback doesn't catch up quite enough to lead it back into stasis. It actually overshoots and come back, and eventually it will reach this sort of equilibrium, but it's often a damped oscillation that's leaving there. And in fact, people have shown that many common oscillations we see in practice result from delays associated with negative feedbacks. There's delays associated with time. And ladies and gentlemen, the beauty here is that when it comes to these feedback loops, we can compose them. We link them together into larger systems, and those lead to patterns of behavior that are sort of compositions or combinations of those. So here, early on, what sort of behavior is this early on in this graph? It's a behavior associated with which of these loops? Positive feedback. And then as the customer base becomes saturated, you get a dominance of this loop because there's fewer and fewer potential customers, and that limits the amount of word-of-mouth sales. This loop tends to dominate eventually as the number of possible people who can buy the iPhone 5 max out, the number of people who are potential customers gets drained, and that's the one that's dominating, no longer this one by spreading to larger number of customers, because there's few potential customers remaining. So here we get a situation where it sort of plateaus out. So this is sort of a composition of the feedback, the characteristic dynamics in the feedback here, and the characteristic dynamics from the feedback here, put into a single sort of situation. So, ladies and gentlemen, I think I'll close my lecture on those with those thoughts. Just bear in mind that when it comes to real-world activities, whether it's your own personal life or issues having to do with projects, maintaining those balancing loops is key for often maintaining the situation in a state that's stable, resilient, and sustainable. Okay? So that's all for today. I think for next time, I was hoping to get to the models today, but for next time, I'm going to actually ask you to build up a causal loop diagram, each of you. Build up a causal loop diagram and bring it to class. You can sketch it out of paper if you want, or you can draw it in Vensim. And in Vensim, you can easily label things associated with polarities of arrows and so on. And I'd like to suggest that maybe I'll just show that for a moment here in Vensim so you can see exactly what I mean. If you were to call it Vensim, this is one of the tasks. Oh man, you don't want to see that. The tasks at which it excels. Here we are in a Vensim model, and we can go and we can put on. Hey, what? Oh man, what happened to my toolbar? Oh man, sorry, I am in bad shape here. My Vensim is disappointing me. Here we go. Okay, fine. No, I don't want to. Thank you. Oh gosh, that's bizarre. Oh, I need to have a new model. That's why. Okay, there we go. Now we're cooking with gas. So here, if I want to have, hunger. Hunger. So I use this one here to introduce a variable, and I want to introduce, food ingested, something like that. I can draw this arrow from here to here, right? And I can use this handle to sort of enlarge it, and I can right-click on this, just like this, and we can label it with a polarity, and I can say where that label goes at this handle, for example. And then since I'm in this mode, this is a modal system, I can draw it back the other way, and I can label that with a polarity that's negative and label it at the handle. And there I've drawn my first causal loop diagram. And to label the nature of the loop, I can go insert up here and comment, boom. Go insert an image. I'll make it a negative feedback loop, and I'll have it be a loop clockwise. There we go. There's my first little diagram. So if you want to, you can use Vensim as I did, and draw a diagram. Otherwise, draw it by hand. Bring it here, and I'd like to interact with you and comment on the diagrams and talk about how they can be improved. Okay. I may also send a video for you to watch by next time so we can use more time in the class for doing exactly that. Look at the diagrams, commenting on them, and you should be able to use them in your first problem set. So there's a motivation to bring them in. Okay? Thanks very much. Oh, one other thing. Be sure to look at the playlist for the class. It's posted on Moodle. Every class, I'm posting videos to there. Keep an eye on it, because the videos automatically, well, not so automatically, but the videos appear there periodically, okay? And just keep track of that. You don't have to be sending out mail saying video X is posted. You can just kind of count that within a day or two of class will be there. Okay? So let me make sure our remote things. Okay. Hey, where are they? Okay, looks like they made it. Um, oh man. Okay. Hello. Wow. It's not working. Okay. People need to speak. Speak. Yeah. What's up?